Section 15.4 in our Art of Problem Solving Introduction to Geometry book talks about problems related to three-dimensional figures. So we're going to have to use all of our knowledge from our study of prisms, pyramids, cones, spheres, cylinders, all that together in this section. At the same time, we may have to incorporate previous skills that we've talked about in sections, in chapters even prior to that. So triangles, squares, rectangles, etc. Okay, so an example problem that you may encounter is similar to this one. So if you consider tennis balls, they are sold in packs of 3 spherical balls, each of an average diameter of 2.6 inches, and it's in a container. The container is in the shape of a right circular cylinder, and all the balls fit snugly inside it. So we assume that they are tangent to the size of the container as well as the bases, and then each ball is tangent to each other. So we suppose that the manufacturer determines that the thickness of the container must be 0.1 inches to minimize cost while making sure that the tennis balls are secure. So we want to know what amount of material the company needs to use to package the set of 3 tennis balls. So if I were to draw a three-dimensional picture of this, it might look something like this. So I have my cylinder, a right circular cylinder, and then inside this I have 3 balls. Again, there's some thickness to the container too, but okay, and so here would be my 3 spheres. Okay, and so now a three-dimensional figure isn't going to help me too much, so I'm going to use that same skill as before and try and model this into 2 dimensions. So if I kind of push this down onto a flat surface, it would look like I have a rectangle. Okay, and then I have circles inside that rectangle. And I think I'm going to extend this a little bit. Okay, so my container is going to look something like this. And again, all the balls are tangent to the sides of the container. Okay, so it looks something like this, and then there's some thickness to it. So I'm going to make another rectangle around this. And okay. So now I know each ball has a diameter of 2.6 inches. Okay, so really what I'm being asked to find is the volume for this for the material used in the container. So the space between these 2 rectangles. Okay, so next what I need to do, and remember that this is a cylindrical can, so it's not just finding the 2D representation, but actually looking at it in 3 dimensions. Okay, so what I need to do is continue to label my diagram. Well, if I know that each ball is 2.6 inches, that means that the height of the inside part of the container is going to be, so I'm going to do height inside is going to be 3 times 2.6, or if you do this out, it ends up being 7.8. Okay, and at the same time, for the inside diameter, we know that each sphere is tangent, so the radius of the inside is just 2.6. Okay, but now remember I also have an outer component to all these as well. So if I look at the outer radius, which is going to be slightly longer, this incorporates the thickness of the can. So the height of the inside, or the outside, sorry, is going to be 3 times 2.8. And actually that's not quite correct, because that would say each sphere has an additional additional 0.1 on each side of it. So instead, the outside component is just going to be the 7.8 plus 0.1 on each side again. So the thickness of this is 0.1. So this would just be 8 inches. Okay. Similarly, the radius here, or I shouldn't say the radius. This is the diameter. The diameter of the outside is 2.8, again incorporating 0.1 on both sides. Okay, so then if I want to determine the volume, I'm thinking my approach here is going to be to determine the volume of the outside, incorporating the thickness, and then subtract out the volume for the inside component where we have where the tennis balls are, and we have a little bit of void space. So if I know the diameter of the outside is 2.8, that means that the radius is half of that, so 1.4. And similarly, for this one, the radius of the inside is going to be 1.3. Okay, so if I want to determine the volume for the outside, again, that's still a cylinder, so I need to use the volume of a cylinder, so that's pi r squared h. But now for the outside, I'm using the outside radius and the outside height, so this is going to be pi radius, we said was 1.4, squared times height of the outside, which is 8. Do this out mathematically, and I got 15.68 pi inches cubed. Okay. Similarly, we can find the volume for the inside, and again, you'll use the inside radius and the inside height. And in this case, the radius is 1.3. You square that times 7.8 and 8. And this ends up being 13.182 pi inches cubed. Okay, so then when you put all this together, the volume required for the material now, this is going to equal the volume of the outside minus the volume of the inside. And computing this out, I got approximately, I should say approximately here, 7.85 inches cubed. And that would be even after you multiply the result by pi. Okay, so again, what I did is took a 3D scenario, changed it down to 2D, found my information in 2D, and used that in the equations for the 3D figures. Alright, and the next problem is a famous problem in mathematics, and it's really, really fun. A spider and a fly. Okay, so what happens here is we have Sally the spider. She's at corner F in this room, and she notices a fly at corner D of the room. And she wants to be able to get to the fly, but she can only travel along the surfaces of the room. So she can't travel through the space in the room. Okay, and it gives us different dimensions here. So we know that BC is 5. Let me maybe label these in blue. So BC is 5, and GH is 6, and DH, so this back wall has height 8, and then we want to know the minimum distance. Okay, well, minimum distance is a straight line, but and the straight line in this context would be the space diagonal. However, we can't travel through the space. We can only travel along the surfaces of the room. Okay, so I'm going to first finish labeling this diagram, and then we will, this is going to be 6, this is going to be 8, and 8, 8, and I think that is everything. So now what I want to do is determine the minimal distance path that Sally would have to take along the surfaces to get to the fly. Okay, so again, Sally is here. Oh, I'll maybe do that in red. So this is Sally, and this is a fly. Okay, so now what I want to do is, again, I want to try to use the same idea that we presented in the last problem where we made this into a 2D model. Okay, to do that, what I'm going to do, and I suggest that you pause the video and attempt it for yourself, but what I'm going to try is to cut this this prism apart. So I'm going to cut along AE for sure. So that's going to be the top of my two-dimensional figure. So here's AE. And I would cut it so that E is over here and A is over here. Okay. Then I have to make some more cuts, and I'm going to cut along AB and EF. Okay, so I have these two sides cut, and then the next sides would be B and F. Okay, and that would be one side. Now for that side, I know that, okay, AE is 8, and I know that AB is 6. Alright, then I'm going to continue to cut as needed and unwrap this prism to get the two-dimensional representation. And this is actually called a net, in case you've encountered that language before. So I'm going to continue to unwrap this, and I'm going to pause the video and continue unwrapping this. Okay, so I just paused the video and created the rest of the net. And so what I did was I continued to unroll the sides around it, and I left it the two tops, or the bases, I should say. I left the bases attached at side BC. So I first made all these the sides, the rectangles on the sides, and then I left the top, or the bases, attached at BC. Okay, so now on my diagram I have Sally being at point F and the fly being at point D. And if I want to determine the shortest distance, well, the shortest distance is given by a straight line. That's not really a straight line, but you get the idea. Okay, so straight line. Now, when I look at this, when I see this, I see a right triangle, where I know that the two legs are 11 and 8 respectively, and I want to determine the hypotenuse length x. So using our knowledge from triangles, I said, well, x should equal the square root of 11 squared plus 8 squared, and so this ends up being the square root of 185, which is approximately 13.6 feet. Okay, so again, in this problem, what we did was we took a three-dimensional figure, and this one was a little bit more challenging because we actually had to construct the 2D representation of the entire figure by unwrapping the sides and forming, this is called a net in geometry. So and so what we could do is, if we wanted to recreate this, we could fold along any shared edges and recreate the same prism. Okay, and then once we got that 2D representation, we were able to look at the minimal distance, which is a line, and make that. So on the diagram, quickly, it would look something like the minimal distance would be from here and then up to here, something like that. That would be this line in red. And that's some problems that you might encounter in section 15.4.